So hi everyone, I'm Christian. I'm a postdoc at the University of Sheffield in AXI, working with Daniel. And since June last year, I've also been one of the DAFNI champions, and my role was particularly with regards to digital twins. So one of the main aims of my championship is to provide a digital twin use case for DAFNI, and this is helpful because it tests the platform's capabilities to accommodate digital twins, but also it informs on new functionalities that are necessary to add on DAFNI in order to accommodate full-scale digital twins and integrate models from different sectors as well. So together with this, we've also, the model and the use case that we've built is a foundation for traffic digital twins in Sheffield, and we achieved that by creating a digital replica of the traffic and identify areas where there might be congestion in the future. As Daniel presented earlier, we're still on a lower levels of maturity because the project just started, but we have plans to take it up the level scale. So first, I will start by explaining the sensor network that we are using. So there are about 640 traffic sensors distributed around Sheffield. And the picture that we have here on the right side shows the actual number of sensors that we have in certain areas. So as you would zoom in, you would see all the individual sensors, but as you zoom out, it only tells you how many sensors there are in each area. And then this is something that you can access if you go to the Sheffield Urban Observatory's webpage. You can see this in more detail. So we have traffic flow data coming from all these sensors every 5 minutes, and traffic flow means number of cars that pass through each point every minute. And for the model that we built, we are harvesting the data since September 2019. You get access to the data through an API call that is supplied by the Sheffield Urban Observatory. And then before we do all the predictions and the work, we do some pre-processing. And the key thing that I want to mention here, because I won't be going to more details later, is the smoothing of the data that we apply, which is just a 20 minutes moving average. So it's a 4 measurement if you want moving average, because the time resolution is only 5 minutes. And there also we have some missing data and outlier detection checks in the process, and I'm going to explain that in a future slide. So the data that we are having, just so that everything that follows makes more sense, I'm going to explain first how we structure it and how we store this data. So we organize it into a matrix format, such that the matrix, the columns of the matrix correspond to different sensors on different days. So we structure the data in 24-hour vectors. So each vector corresponds to 1 day of traffic data for a particular sensor. So, and if you look at the different rows of the matrix, there would be different time slots during the day, during the 24-hour interval from midnight to midnight. And the reason why we do that is because we observe that there is a pattern that keeps repeating in traffic behavior over a 24-hour interval. So every day, if you look particularly for Monday to Friday, the traffic pattern is very similar, Monday, Tuesday, and so on. There might be differences between weekdays and weekends, but we take that into account at the later stage. But in general, the pattern keeps repeating every 24 hours, and we want to exploit that. Because we structure the data in this way, in order to have an updated, pre-processed historical data set, we need to run this model that updates the data set every 24 hours. So at the end of each day, the model needs to run, and then it will add a new set of columns for the last day of traffic in particular locations in the city. So for all the sensors that we have. And the way that works is represented with this diagram on the left side. So you would get the data for the last day of traffic from the API call. And then you first identify the sensors that are active. So sometimes not all the 640 sensors would work. So first you check which ones are working and which ones are supplying the data. then you check if there is a missing data, and we have a threshold. So if it's like 90% missing, then we don't necessarily use the data that we have. If the number of measurements is lower, then we try to interpolate some of this data. We also do some outlier detection checks. Things like some sensors might report like 0 values for a 24-hour interval, and we think that that's not correct. So we disregard that particular vector for that particular sensor on that day. And there are other checks that we've implemented here, and then we apply the smoothing that I talked about earlier over all the vectors. And then you would add the new set of columns into the old matrix, so that the matrix is now up to date for the last day of traffic. And this data gets then fed into a traffic forecast model. And this is not the only data that comes in. So in addition to this pre-processed historical data, we have another data stream coming from the same API call, but this one contains the last, let's say, k+1 values. And what I mean by that, I'm going to explain in more detail in the next slide, but basically from the current moment when I try to make the prediction, I look back and see what are the most recent measurements, and those are the ones that I'm going to use to make my predictions as well. Of course, the same processing that we did for the historical data is then repeated for this like most recent data values, because we want to ensure consistency between the two types of data, and we want to process them in the same way later on. And then the combination of processed historical data and processed real-time data goes into this forecast model, and then the results are sent to custom visualization that we've implemented on DAFNI. And also there is a new data set generated on DAFNI, such that people that want to use the outputs of the model can then just access this data set. The same is applied for the pre-processed historical data. So if someone wants to use this pre-processed data set, it's also available on DAFNI as an independent data set. So a few words about the forecasting model. The real-time or the latest values recorded by the sensor. So all this process is explained for one particular sensor. So we assume that it's 2 p.m. at the moment, current time, and we want to do prediction for one sensor that we're interested in. So you would download first the latest measurement, let's say from 2 p.m. to 6 a.m., so about 8 hours of traffic. And the objective is to fill the gaps here and say what are the values between 2 p.m. and 3 p.m. And we have the historical data that is pre-processed here as the input, one input data, and then the other input data is what comes from the latest values. So the first thing we do is then we trim the historical data to align it in temporal domain, which means that we cut the historical data set and we keep only the part between 6 a.m. and 2 p.m. for all the dates and all the sensors that we have processed there. And then we do a selection process. And this idea with the selection process is that there is a pattern that we can recognize in the last 8 hours of traffic. And we want to identify in which days in the past and which sensors we can find a similar pattern. And then we have the selection process that selects a subset of these historical data that is correlated with what happened today. So previous days and previous locations in the city where the traffic pattern was similar. And the assumption that we calculate the prediction based on is that if what we've seen today in the last 8 hours correlates and is very similar to what happened in the past in particular days and locations, then whatever is going to happen in the future today, it's also correlated with what happened in the past in those days. And because in addition to this 6 to 2 p.m. interval that we have in the historical data, we also have the extra part between 2 and 3 p.m. because this is historical data. So this has happened in the past, so we know what happened in the past between this 2 p.m. and 3 p.m. interval for the sensors that are correlated. So to do this, we train a machine learning based regression and we give the input data, the 6 a.m., 2 p.m. interval from historical data, and we train it to predict what happened today, earlier. And then we shift that, and we give the 2 p.m., 3 p.m. input into the trained regression, and that will produce a forecast for the time interval 2 p.m., 3 p.m. today. So yeah, that is the quick overall view on how we do the predictions. That machine learning based regression, we try to do it with multiple approaches, and we found that the Gaussian process regression works best in terms of performance, but also computational power. That's also something that is worth taking into account, particularly as we were aiming to scale this up. So it might be that it takes only 1 second to do the prediction for one sensor, but once you have 600 of them, then you can't really do this on a normal computer. So we're relying here on DAFNI's computational power to scale this up and run parallel sessions of the process that I just explained, such that we do predictions in parallel for all the sensors. In terms of performance, I won't spend much time here because I am aware of the time constraints, but we checked the performance of these approaches, and they are on par with what we've seen in the literature. Again, it's kind of difficult to compare one-to-one because of different smoothing processes that are in some papers, and the data set is also different, but the percentages, because we calculate the error as a percentage, average percentage over a 24-hour interval, it seems to be similar with what we've seen in the literature. It's worth noting that for some sensors, the predictions are better because the pattern follows like a pretty normal traffic pattern. But once you start having congestion scenarios, like some of these particular days that we're looking here, then it becomes more tricky, and that's why you would see some sort of decrease in performance. But that's exactly what we want to do, to identify congestion. So this is the error that we need to look at. A very quick slide on how to upload this on DAFNI. Tom has already presented the main steps, but because one of the parts of my championship was to accommodate MATLAB models on DAFNI, I have a brief slide on this one. So because the model that I built is in MATLAB, so you start by creating your MATLAB model, and in order to upload it, the easiest way that I found is to create a Linux executable version of the model. So if you have MATLAB installed on a Linux machine, is just clicking a couple of buttons in MATLAB, and it will produce a small executable file of your code. And then the advantage of using this approach is that the Docker container that you have to build is standard. So you take this already built Docker container with MATLAB runtime, so the instructions to do it are the same, and you just copy your code in there, and it will automatically create a Docker container that works for your code. And then, as Tom said, you have to create that model definition file, which is a text file that explains what the model does and what are the input parameters and data sets. And then these two, as you just have seen, you upload them onto DAFNI, and then you integrate your model in a workflow. The key message here is that we can accommodate MATLAB models, and the main advantage of using the runtime-based container is that you don't need the MATLAB license to run it. If you do it in other ways, MATLAB, as you know, it's a paid service, so you might have to pay a license to even to run the code on DAFNI, but using the MATLAB runtime container, you don't have to. So as we integrate the model in a workflow, and then the output of that workflow can go into a visualization, and the one that we currently built for the digital twin for traffic looks like this, and you have like a colored circle at the location of each sensor, and this color of the circle depends on the traffic flow that we've predicted. And there is the slider at the bottom that you can move and go from the 5 minutes ahead prediction to the 10 minutes, and then all the colors will adjust based on the prediction that we did for 10 minutes, and so on and so on, until you go to 30 minutes. At the moment, if you go on the platform and run the code, it's only going to plot one of these dots because the code runs for one sensor. But we are in the process of scaling it up, and it will it'll be a matter of just running the code in parallel for multiple sensors. So a few plans that we have, like I said, to scale this up by calculating predictions in parallel for multiple sensors. We want to have the model that updates the pre-processed data set run automatically in the background. And we are aware of the data that we are using now. It's only 5 minutes time resolution, and it's not always reliable. Some of the sensors, like I said, are inactive. So we are looking into adding more types of data, particularly occupancy, which is much better for predicting congestion. The idea would then be to integrate this model in a real-time user interface, such that you don't have to go back to the DAFNI platform and click the button to do the prediction again, but you would have an update button on the interface, or you could draw some regions of interest from Sheffield that you want to get data from and prediction from, and then you can create your custom output data set that you want to use for a different model maybe. And then, of course, as we go up into the maturity level, we see this as being integrated with some interventions together with City Council maybe, such as adjusting the traffic light in areas where we predict that congestion is going to happen. So that's something that we're very much interested in doing as we develop the model and we get more data and more functionalities on DAFNI. So then the visualization that I have here might suffer some changes. There might be new functionalities added as we go ahead. And finally, I just want to acknowledge the funding and the championship project that was supported by DAFNI. Been a great opportunity for me to work on this. The DAFNI technical team, which has been great in helping me throughout the process of learning how to use the platform, particularly Rose and Tom, because I've worked more closely with them, and Patricia from the Sheffield Urban Observatory, which was very helpful in setting up the API call and sorting out some of the issues with linking DAFNI and the Urban Observatory. And that's it from me. Thank you very much.